This meeting is being recorded.
In section 14.4, we're going to review the second signal characteristic that you should consider when you're looking at a spectrum. So the intensity is indicated here as that characteristic. So the strength of the signal, aka the intensity, can vary. So we see here our signal is based on the percent transmittance, and therefore something that is down around 10% here, transmittance, we would consider this a strong signal. So it almost goes all the way from the top down to the bottom, this first signal shown here. So it does not have to be quite this intense, quite this strong to be considered a strong signal, but you can see that they are relative to one another. So this here is considered a weak signal on the right. So we can see that the percent transmittance is somewhere around 70%. So this, again, we would consider a weak signal. So let's take a look at why this might be the case. So we know that intensity of our signal depends on the dipole moment, or just the fact that we see a signal depends more so on the dipole moment. And when a bond undergoes a stretching vibration, as we're told here, the dipole moment also will oscillate. And we say that generally the larger the dipole seen in a bond, the more efficient that bond is at absorbing infrared radiation. So the intensity is directly related to that fact. So overall, we could generalize that the greater bond polarity, so therefore we look at the two atoms that are involved in this bond, and if there is the greatest difference in electronegativity, we would see that there would be the greatest bond polarity. So the stronger the dipole moment of our bond, the stronger the IR signal. So we can see here that the CO stretch of this carbonyl has, this value shown for its dipole moment versus the dipole here for a CC double bond is much less. So there is a little bit of polarity because we don't have a completely symmetric molecule here. But again, the bond polarity is what directly causes this IR signal to be greater or less depending on the two atoms involved in that bond. So here's again a specific example now for the intensity that can be seen. So we can see that the carbonyl stretch shown here, the intensity is much more than the general strength of a CC stretching signal here. So we can compare those intensities that we saw here, right? And we can relay that reasoning to this spectrum shown here. So if we have a symmetrical bond, so this molecule here, this CC stretch that we might be looking for, would not give a signal. So we see here there's no signal in the range where we would normally expect this carbon-carbon double bond, a little bit around 16 to 1700 in that range, but it's not present because this molecule is symmetrical, and therefore that CC double bond does not experience a dipole. So that is why when we have a symmetrical molecule, sometimes we do not see a stretching frequency observed in an IR spectrum. So we need that dipole. So this slide here gives us some additional notes about how the intensity is interpreted in signals. So we know that stronger signals are observed when there are multiple bonds of the same type vibrating. So we can have multiple signals contributing to that same region, that same wave number. So we generate stronger signals when they overlap. We know that CH bonds, not very polar, but they give strong signals because usually there's a lot of these in organic compounds. So again, that's multiple bonds of the same type vibrating at the same frequency give a stronger signal. And lastly, we have here, if we need to determine something like blood alcohol levels in a complex mixture like blood, this signal strength can be helpful when we analyze ethanol, right, alcohol, in intoxicated individuals. And this is able to detect these low concentrations, right, inside of a complex mixture. So again, these are just some additional notes about intensity. And we'll continue with the last characteristic, the signal shape, on our next video.